Yeah, so welcome everybody to this session on the functional requirements for multi-vendor, multi-terminal HVDC systems. This is mainly the results of the interoperable deliverable 2.1 that we present today. So it's Paul and me presenting and Mario doing the introduction as a work package 2 lead. Just to say that we are presenting, but of course it's a joint work with all the vendors and TSOs and the PPM developers involved here. This is quite important to highlight. Then we have an introduction from Mario for 5 minutes. Then Paul and me will take over with the main results of deliverable 2.1, and then we reserve some time for Q&A. So I would like you to note down the questions. You can even online put them directly in the chat, and then we go to the Q&A session, and we make sure that we have enough time to go through them after the presentation. Yeah, Mario, floor is yours.
Okay, good afternoon, everyone. Can you hear me? Can you hear me? Yes, okay. So unfortunately, I cannot see you. So welcome to this session from my side. My name is Mario Andreco. I'm talking from the TenneT offices in Bayreuth in Germany. Unfortunately, due to other commitments, business commitment, I could not be there. So what I would like to do is a little bit give you an overview of the work package 2 in InterOPERA, what we are trying to do, why it's important for us. And then I would give the floor to Pascal and to the other colleagues from SuperGrid who are leading this task and this deliverable, to give you more details of what it is about. So next slide, please. And so what we are trying to do also next, just open it up all. Yeah, so what we're trying to do in InterOPERA in general is to go out from what we have today, single vendor projects, towards, let's say, multi-vendor approach. And multi-vendor means in principle that we look together with our partners, TSOs, let's say, in the project, or HVDC OEMs, wind turbine OEMs, project developers, how we can go from fully closed HVDC system to different building blocks, and what are the requirements for these building blocks. So what is the state of play today in general for point-to-point, but also for multi-terminal HVDC systems? We impose AC side requirements based on regulatory frameworks. So let's say that we have on European level the network code HVDC and its national implementation in various member states across Europe. Some of these requirements are detailed. Some of these requirements are, let's say, fully harmonized in Europe. Some are non-detailed, non-exhaustive, which gives the room for national implementations and for the TSOs on project-specific basis. So this is the status quo. What we want to do is we want to split it. We want to open up, let's say, to from a single vendor approach, as you can see to the right side, where we have defined the main, let's say, building blocks of an HVDC system. For example, HVDC station, DC switching station, and what these tasks and what this effort in InterOPERA, and as said by Pascal, it was not SuperGrid, it's all industry in principle. No? We try to find a consolidated view on the DC side. So as I said, on the AC side, this is fully regulated, fully understood today, it's mature. On the DC side, if we want to make up, to open it up and to ensure that different OEMs could provide solutions and could be connected and could be interoperable by design, by specification, we need to have certain level of these building blocks of requirements, which are both technology agnostic, of course, we cannot prescribe solutions, and also functional and also quantitative. So that's all what Pascal will show you today. The ultimate goal of the project, I think, you have heard, I'm sure, to other presentations. Next slide. So the ultimate goal is, of course, we will. Next slide, please. Once we develop, let's say, functional requirements in the phase 1, and as I said, the project is let's say, have 2 phases. The first 2 years is mainly on preparation of the demo, mainly developing functionalities and agreeing. This is very important not to forget that InterOPERA is building also a consolidated approach and a whole industrial approach which all stakeholders accept. Let's say during the first phase, functional requirements, which in principle will be the basis for future tendering, procurement of multi-vendor projects, and also functional requirements mainly on the DC side. This is a new thing. Which of course grid planners need, and of course TSOs need to procure. During the second phase of the project, I think we starting from next year, I think all the functional requirements will be detailed by the OEMs, will be developed in what we call detailed specifications, and will be brought to the labs, so that we can prove that it is possible and is risk-free. In terms of all kind of potential technical risk, means all kind of interactions, incompatibilities that we may have. So this is during the second phase of the project. Of course, today we will focus only on the first part, and Pascal and the colleagues will explain, in principle, everything about the results of the consolidated effort. And I repeat it the third time: it's a fully consolidated effort of the partners to reach the deliverable that was published. Next slide, please. Yeah, this one. So this is the timeline, and I will leave the presentation to this point. So we have reached the first milestone after 18 months approximately from the start of this task. The first version of the functional requirements are agreed and are set, let's say, are published, and we will be working till month 24 from the start of the project, end of this year, to finalize the first set of functional requirements, also provide maybe potentially some ranges of parameters, and with, of course, a big disclaimer. And this will be based for the test specification of the demo, and of course will be tested in the phase 2 of the project. In parallel, we have also activities to develop the test protocols for the testing of the systems and subsystems, and this is also ongoing during this year. So that's all from my side. So thanks for all of you who are there, and I leave the floor to Pascal to continue and to present you the main parts of this work. Thank you.
Yeah, thank you very much, Mario, for this introduction, and to highlight also the importance of the DC grid requirements that we try to define here. So first of all, the deliverable. So as you just showed the timeline, in month 16, we released a deliverable, first version of DC side functional requirements. And you can see here actually the report, and this is also how we worked in this task. So we split it into several work streams, as it is highly interdisciplinary. So we are not only tackling continuous control aspects, but also sequential control, and also DC grid protection, which gained quite some important part here in this task, which was not initially planned, but as we talk about expandable DC systems at some points, if you want to eliminate the DC faults and to limit the outages on the DC side, we need to think about how to put in place DC circuit breakers or fault separation devices. So this deliverable is publicly available on the InterOPERA website. And then quickly reminding the objectives of this functional framework, it is quite important to say that we want to, first of all, have a common understanding. So this took quite some time to get everyone on the same page, so to say, and that everyone understands the same thing when we say the same words, actually. So this was quite a challenge already among all the different partners in the project. Here, we want to develop basic rules for protection, control, and DC grid operation. Then the highest objective is to be technology agnostic, so not to exclude any vendor-specific solutions without justification. So we want to open up this design space that you can see on the left as much as possible, while still ensuring interoperability by design. And this is quite a challenge, of course, because how to ensure that the grid will operate in a stable way with all those different solutions put in place in the DC grid. and while also avoiding overspecification due to cost. And you can see here on the left side that each functional requirement that we define may limit to some extent the design space, even though it's coming from a different area. So the DC grid protection functional requirement could, for instance, limit or define the design space also for a control response, for instance. Because as we know, DC reactors, they are also having quite some influence on control responses, etc. So they are all some kind of interconnected, and this is of course a challenge to define this in a consistent way. So now when we think of defining requirements, we want to assign them to different subsystems. So here you can see the HVDC system, which incorporates different subsystems. So converter is maybe the most straightforward one. We can also see passive elements on the very right side, which are transmission lines, cables, overhead lines. And then a central part is, in fact, the DC switching station, mainly responsible for all grid operations. And a common understanding in our framework here is that the DC switching station is responsible for all reconfigurations in the DC system. And the AC/DC converter station is to be seen as a energy conversion device, mainly responsible for controlling and adjusting the power flow and the DC voltage. And then we have unavoidably AC connected parts, which are mainly the PPMs at the offshore side, which are inherently connected. And of course, we need to make sure that the requirements that exist, as Mario said, on the AC side, they are not in conflict with what we define on the DC side. And so now, Paul, you can take over.
Yes, thank you, Pascal. So as already mentioned, the work in this task was divided into 3 main work streams. One of those is the continuous control. As Pascal said, one important aspect was to share a common understanding of what we actually talk about. And when it comes to continuous control, there is a lot about the control hierarchy and to which level do you assign which kind of function or functionality. So the top layer or upper layer for continuous control would be an integrated AC/DC grid control. So typically the TSO related level. So this is not part of the DC grid, obviously, but it will give commands and inputs to the DC grid. So it is fully relevant here. And then when it comes to controlling the DC grid, we have this coordinated layer that we can call DC grid controller that will have the task to take the commands that comes from this AC/DC layer and translate and transfer them to the relevant subsystems, in particular the converter stations. So that typically includes all functionalities that require or benefit from some sort of coordination, in particular power flow related functions, secondary voltage control, control mode coordination, and so on. And then when it comes to the implementation of those references, this goes down to the converter station, divided into this station level, as you see here, and unit level for typically primary DC voltage control and control mode implementation and so on. So the coordination of those different stations and functional level has a lot to do with defining the appropriate voltage ranges within the grid. So meaning that all the subsystems have to share and align on some sort of voltage ranges. The 3 main concepts that were distinguished are this transient part, which is typically the voltage that will be observed just after a fault or disturbance. So this is typically rather a protection matter more than a continuous control topic. And then you have the dynamic range, which is where the voltage is supposed to be limited after a contingency based on primary response of the converters. and then the steady state ranges that you can further define with a continuous voltage band, which would be the largest one, which is a band where the grid can operate indefinitely, but with reduced margins typically. So for a steady state operation, you typically aim for a narrower band, which what we called normal operating range. So this is typically the kind of the framework we agreed upon for voltage ranges. And then for the specific values, this is obviously a different task, which is more project specific. Going more into details about the primary response of the converter stations, one important topic was to agree and clarify what we mean and expect by a droop control. We come up with this multi-segment droop definition that is also kind of similar to concepts you find in the AC world with frequency sensitive mode and limited frequency sensitive mode that you find here translated with DC VSM and LDC VSM. So this means that you would have one behavior around the operating point, this limited this voltage sensitive mode related to ordinary disturbances or fluctuations around the operating point, and then some limited DC voltage sensitive mode for both over and under voltage, which are more related to larger disturbances and contingencies. And all those requirements are for static behavior, and we also tackle dynamic requirements.
Yeah, and what we can say from the static behavior, we can say that if we have a given disturbance in the DC grid and we lose some power, then we know where the system will end up. So this is something that the operator has defined by choosing the droop constants and the way the converter responds to the disturbance, or each of the converter. However, what is a bit more uncertain is how the converter or every converter will behave in a dynamic way. Here on the left side, you can see that there might be completely different responses to disturbances. There might be one converter that is responding extremely fast, but with a high overshoot, or another one which responds a bit slower and highly damped. So all these different response times, they need to be somehow convenient to the response that we would like to have in the DC system. You can see in CIGRE brochures and other technical brochures that different droop schemes exist, and they also have an influence on the dynamic behavior. However, here it's not the intention to define or to prescribe one implementation, because this is once again specific to the vendor. What we like to do is to implement or to define a desired behavior of the converter according to a disturbance, and we would like to prescribe this at the DC point of connection of a given converter. We know that it mainly depends on the droop gain, for instance. It depends on the DC grid, DC reactor sizes, different converters in the grid, cables, and the particular controller design. So what we are currently working on, and this is quite a major task and maybe even quite ambitious, is to first say, okay, we would like to have some kind of a time response of a converter, where we maybe find something similar to what is done in AC systems, which is a second order response with a given dead time, step response time, settling time, and also some kind of a tolerance limit where we would like to end up. Then what is crucial is to define a DC grid equivalent. So how can we estimate the DC grid behavior at the DC point of connection of a given converter station in quite a simplified way, quite similar to what is done in the AC grid, where we have also AC grid equivalents, and we define the desired response on the AC side by applying such kind of AC grid equivalent. So this is something we are currently working on, and this will be like this investigations that will be integrated in the last part of the deliverable, which will be released end of this year. So we also do some kind of technical investigations based on generic models in this case. And so this was everything related to the continuous control. Now Paul will take the sequential control part.
Yes. So one other huge topic that we had to, let's say, gain a common understanding again is sequential control, meaning everything that is related to the definition of the connection modes, the different connection modes you can have in a HVDC system, and how you control them in the, for planned reconfiguration. So not protection related actions, but yes, planned reconfiguration of the HVDC grid. The framework we proposed is based on a different aggregation that was, for instance, introduced in the SENELEC document. And one important aspect first is that all, let's say, switching functions are put into this switching station, which is not or different from the converter station. So the converter station itself does not have any switching functions relevant for the grid. Obviously, it will have internal switching capabilities for its own need and protection and so on, but everything that is of interest to reconfigure the grid will be part of a DC switching station. And then how to describe the possible arrangements you can have in a DC switching station is based on this switching unit concept, which is basically an aggregation of all the switches you can have between two connection points of the same pole. So, for instance, between this positive pole at the output of the converter station and the positive pole bus bar. And same goes for the neutral. And then depending on the, let's say, I mean, you can apply it to different units. So switching units can also play the role of a bus coupler and also can also connect transmission lines. One of the interests of doing this is that irrelevant of what there is actually inside a switching unit is from a, let's say, a higher perspective, either closed or open, basically, even if within it can imply different more specific actions or switch gears. When it comes to the sequential control architecture, so the way to control this different connections mode within the grid, we find again this kind of layering with an upper level being either a DC grid control or a control room that can trigger reconfiguration commands, going typically mostly to the DC switching station, then transferring them to the different switching units it is composed of. And those commands are, as I said, simple, basically open and close commands, which kind of simplify how it is, how it can be understood. To some extent, it can also communicate with the other components of the grid for simple actions, like just be ready to be connected and stuff like that. One important thing on this diagram is that the horizontal communication is deemed exceptional, meaning that if switching station, for instance, was to have knowledge of what's happening on the converter station, you should rather go through this communication bus, actually, rather than through horizontal communication. Obviously, if there is a specific need to go horizontal, it can be done, but the rule should be to avoid it. And as I said, this is for planned reconfiguration, so speed requirements are unlikely to to be very critical. Going a bit more into details about this switching unit concept. So as I said, it's from an upper perspective, it's basically what can connect two other units, so converter, pole of a converter, pole of a transmission line, and so on. And it's basically closed or open, and it can also ground one of those units. We wanted to go away from detailed description of the switches that are inside and so on, and rather keep it as functional as possible, as already introduced by Mario and Pascal. So all switching units will not be the same. Some will have very rich and complex capabilities, where some others could be very rustic, and those different variants can be described by different functions. So when it comes to, for instance, opening, all switching units could open, but some could open fault current or line current, and some could open residual current, and some could even open only without voltage, things like that. And then the specification of the switching unit can be done then based on these kind of functions. And then the manufacturer, based on this, can come up with a detailed switchgear description and implementation of switching unit, but this is obviously his own choice to satisfy to the requirements in certain ways rather than others. And so this is the main outcome of this sequential control workstream. And finally, I will give back the floor to Pascal for protection.
Yeah, thanks, Paul. So yeah, the last part is indeed on DC protection. Here we have two main things to tackle. One is the DC fault write-through of a converter station, and the other thing is how to ensure that we define the fault separation requirements of the DC switchgear. The objective is to describe them in an independent way, mainly to ensure that the switching station is not responsible for any converter operations and vice versa. So this means that the DC fault write-through profile shall be verifiable at the DC point of connection of the converter station. But as you can see, there is also there might be a DC switching station right in front. So we have this direct interdependence, and this was one major investigation that we did in this deliverable. It is important to keep in mind what the DC fault write-through profile specifies and what it does not specify. So it shall ensure that the converter has enough withstand capability to write through DC faults while the primary protection is operating. So primary protection means the fault separation devices, the time it takes to eliminate the fault. Then the converter shall ensure that it can resume stable operation after the DC fault write-through is over, so after the fault has been separated. And if there is a malfunctioning of the protection of the fault separation, then the converter shall also be able to safely disconnect by tripping, for instance, the AC circuit breaker. However, it shall not ensure that there is an activation of primary protection, because this is done by protection relays. There are protection functions, fault detection functions that are foreseen to trip dedicated switchgear. And this is not done by the DC fault write-through profile, similar to AC systems, in fact. And then what is also not described here is how we would like the converter to serve the DC grid during DC faults. Similar to AC, where we have, like, for instance, reactive current support. This is an independent requirement that we do not describe here with the DC fault write-through. We had a quite important discussion how we would like to describe it. We saw that there are different approaches, how you can see here in the table. One is a design-dependent approach, where we define together the DC switching station requirements and the converter requirements, and we match them such that both of them can operate safely. However, this then needs to be done jointly, and we should keep in mind that here we have a multi-vendor system where the switching station could come from a different vendor, and so all the specific parameters might not be known for the converter, and they should be able to be procured independently, in fact. So this is why here we try to describe it in a generic way. So generic means that the fault right-through profile is applied at the DC POC independently of what is inside the switching station. If there are huge inductors, low inductors, fast or slow DC circuit breakers, this is just similar to AC systems, where we also do not distinguish between fast or slow AC circuit breakers, to make sure that we do not exclude any circuit breaker technology. We then also thought about how to specify it, in which quantity. There are current-based and voltage-based. The advantage of voltage-based specification is that we do not touch any sensitive requirements of the converter itself. For instance, the overcurrent capability of the IGBT modules, they might be quite different between the vendors, and specifying this to a certain level of overcurrent may risk to exclude some kind of existing solutions already. So this was a major reasoning why we described it in a DC voltage-based and in a generic way. And I will try to explain this further now. So you can see on the left the DC voltage fault right-through requirement. The solid line represents connection requirements. So everything beyond this line, the converter has the right to disconnect. And then you can also see the dashed line, which is the limit between the continuous voltage operation band that Paul presented earlier, and everything that is outside this continuous operation or dynamic operation voltage band. And whenever outside dynamic operation voltage band, the converter is not requested to control anymore to be controlled anymore. We also know that half-bridge converters have very limited control capability when they see important DC voltage drops. So this is why in this description we allow temporary blocking of the converter. You can see that there are some characteristic values assigned to the DC FIT. One is T-reg1, which is the voltage recovery time, which is somehow associated to the maximum fault utilization time of the DC switchgear. And then after having assigned all these functional parameters that you can see on in the upper table, there are some inevident design parameters which are left open to the vendors, and this is on purpose because we know some of them are quite critical. So we wanted to include a maximum of different solutions which might be quite performant, such that we do not specify an overcurrent capability of a converter. We do not specify DC or arm inductor sizes, and we also do not specify if the converter needs to have a temporary blocking function or not. So we do not say this is a temporary stop function or a continued operation function. And maybe let's go through an example. So here we see voltage drop at the DC POC of the converter, and whenever we are below this dashed line, the converter is allowed to temporarily block. And this is, as I said, optional. However, when there is temporary blocking, of course, it needs to be ensured then whenever the fault is cleared and the DC voltage recovers to the dynamic voltage bands, the converter is able to first deblock and also to resume stable operation. So this is important. Then now the temporary blocking is quite new, and I think it's maybe important why we have chosen to describe it this way. When we think about DC faults, as I said, half-bridge converters have very limited control capabilities, and continued operation may impose major design constraints on both the circuit breaker and the converter. And now we have three axes that we can tackle to have a better performance. We could say, okay, we will impose a high overcurrent capability of the converters. We could also say we impose a faster fault utilization time of the DC circuit breakers, or we increase the DC reactor sizes to reduce actually the increase of fault current, that we do not reach the overcurrent capability limit of the converter before the fault has been neutralized. So each of those options, they have limitations. The first one may exclude some converter solutions. The second one may exclude some DC circuit breaker solutions. So we should not maybe should not limit it to very fast DC circuit breaker options. And yeah, the third one is a bit more complex and needs to be studied case by case. But we know the tendency is that if we have high inductances, we get a slower response time, and this might affect the overall controllability of the DC grid. So then the temporary blocking has the possibility to significantly reduce the DC reactor size and may be kind of an attractive option to run through DC fault transits. So now we talked a lot about the DC FIT of the converter. The requirements associated to the switching units in terms of fault separation are actually quite simple. So here we only prescribe to say that the fault current shall be interrupted for all ordinary contingencies that the TSO has defined for a dedicated switching unit to interrupt within the maximum fault authorization time, which is a maximum time limit global system parameter in the DC grid. And here, once again, it is important to highlight this split of responsibility between the switching station and the converter station. So the switching unit cannot be responsible in a generic approach for satisfying any converter operational behaviors, because these are different independent subsystems which have independent functional requirements. And this is the end of the protection part, and maybe just a quick glance on what we do currently. So in the last months until the end of the year. So there are two major activities which are tackling the dynamic control requirements and how we can come to a DC grid equivalent definition, how we can ensure that we have some kind of interoperability guaranteed by design based on a good DC grid equivalent estimation in time domain. And on the DC fault ride through, we tackle a bit what does it mean when the converter temporary blocks. We apply this DC fault ride through proposal to as a standalone test, and then also verify on system level if the requirements are still satisfied. And we also have some other initiatives. For instance, we are quite interested in how temporary blocking reflects on the offshore grid with a converter which is in VF control mode, and then leading to a current or temporary islanding of the DC connected PPMs. We are also looking into the MTDC grid operation, so how the DC grid controller interfaces with all these subsystems, and defining the interfaces and the topology of DC grid controller. And then also the initiative of insulation coordination and DC system grounding is quite important and fundamentally different to existing point-to-point systems. So this is also one activity that we started and which will be incorporated in the updated version of the deliverable. Yeah. So that's all. Yeah. So thanks, and we are ready for questions.
I have a question about the.
Could you please say your organization and your name for those online?
Simon Beckler from Transnet BW, German TSO.
Yeah.
Germany. About the allocation of all the switchgear of the, let's say, DC side of the converter station to the switching station. Maybe you can put on the figure, because that's good. So that means that's for a typical HVDC converter station, this would be included in the converter station here, this switching station. So and by this definition, you say all the switching units will be in a switching station.
Yeah.
but in reality, there will be certain measurements, current measurement, voltage measurements, which are in the switching station that are actually required for converter control. And how would this work? Only the vertical communication is allowed based on this next slide, for example. But I think this might be quite challenging.
Yeah, I think so. The main advantage of this is to increase modularity. That let's say the converter station does not have to provide what comes after it, basically, and can plug to any kind of switching unit or DC switching station. So as was introduced at first, this is actually a rather vendor idea than our own idea. So vendors are typically comfortable with it, and then it was raised that for some specific case, like typically measurements, if you need fast measurements from the bus bar, in some cases you could have horizontal communication, but this is more, as I said, exception to the rule based on a specific need, rather than the computer station plugs a lot of wires to the bus bar and it's a mess. So it is still possible if the need is there.
And if I think I want to, the switching station has disconnected the converter station, and now I want to have STATCOM operation, decoupled mode, for example, then I would need some certain switching equipment in the converter station to have a grounding there.
Yeah,
that would allow it, because
so yeah, typically you can either look for grounding through there. Through the if you can still have access to the neutral bus bar, you can find out running there, or the converter station for its typically the STATCOM operation still has access to its own grounding. But for instance, to ground the neutral path of the entire HVDC system, you would not look for it in the converter station, but rather at the switching station level. So that's the logic behind.
I have two questions online from Vinod Kumar. So Vinod Kumar, if you can hear me, you're allowed to open your mic and ask the question yourself, or if you want, I can read your questions. Okay, so I think I will read your questions. Because you're still mute. It's Vinod Kumar from Hitachi Energy in India. He's asking, the first question was about the overall control architecture. He's asking, where does the AC/DC load flow controller sit in continuous control layers?
The AC/DC load flow?
Well, where does AC/DC load flow controller sit in continuous control layers?
I would say AC/DC load flow can only sit in AC/DC grid control. Like if you have to know to a large extent what's happening on the AC side, and then this layer would provide power orders, power references, and power schedules to what is expected to go through the DC grid, and then you need a DC power flow computation, which can typically sit inside the DC grid controller. So that's the logic we imagine.
Okay, and second question from Vinod Kumar: is PPM control communicated to DC grid control? Is it economical considering the ambiguity on the location of the DC grid control? Maybe a few 100 or 1,000 kilometers away from the PPM.
I think it depends a lot on what kind of control we are talking about. At some point PPM would need to have some comments from either distributed control or AC/DC grid layer. So in that sense, it comes from far. For fast action, such as curtailment, several options, of course, are on the table. One is direct communication between the offshore station and the PPM, which would be the fastest in the sense that it is the closest. But it would not be coordinated. And if you think about a larger system with several PPMs, several stations, and so on, understanding what you have to curtail by how much is a more complicated task. And in that sense, it can also benefit from a coordinated approach. So for only speed aspects, maybe you want to have this local approach. But if you want to have a smaller and more efficient way of controlling the PPMs, in particular when it comes to curtailment, then it's beneficial to go through a distributed control.
Okay, I hope that answered your question.
Is this a direct comment to this?
No.
No?
No.
There are some other questions, but yeah, let's take your
If it's finished, then I'm listening to Better TransCPW again. The DC equivalent.
Okay, sorry, it was a comment.
Just a comment directly to this, but from CIGRE. I mean, the PPC is anyway connected to a TSO. If you don't have a good DC grid control, somehow you're going to be receiving set points and communication with TSO anyway.
So by connection, it's not so that the PPC will still receive signals from the TSO.
Yeah, so in that sense, it doesn't change much, I guess.
Mm-hmm. Yeah, exactly.
Yeah, sorry.
Okay. For the question regarding the DC grid equivalent, do you present in the program any ideas how it might look like and how this can be derived by the system operator? Because on the AC side, it's quite straightforward. You make some short circuit current calculations, and then you have the easiest way a voltage source behind an impedance. But how will this look like in a DC? How can this be determined?
Yeah, so I think you can hear me now, also online. So the question was regarding the DC grid equivalent for continuous control. How can this be derived with regards to AC grid equivalents which are already existing and where we know which assumptions we take, if I understand correctly. So yeah, this is something we investigate. The DC grid equivalent should take into account all the configurations, so we can make minimum assumptions on the configuration. So in the worst case, the converter could be connected to a single other converter, then it would be point-to-point configuration, and it should still satisfy the dynamic control response in the same way as it would be connected to a multi-terminal system with an important number of cables and converters connected. So we try to provide this or investigate this minimum and maximum range. We also try to investigate how other converters actually affect the DC grid oscillation during dynamics. So to which extent, how far do we need to go to represent the DC grid? Do we need to go until lower control layers of distant converters? And yeah, I think we already have quite some interesting results there. This is ongoing. I don't want to say too much, but yeah, we will address this in the final version of the report.
But as far as I understood it, it's not just built out of it has to have a certain control and dynamic behavior built inside.
Not necessarily.
Okay.
I mean, in AC systems, you also do not represent each and every generator response or converter response. You have so many different elements integrated, and this is also the objective a bit in the DC grid. Yeah, and then what is a bit distinguished is the transient response, so the higher frequency oscillations, interactions of different converters, and this is a bit apart from this response time, because the response time is a low frequency event, let's say. So yeah, we try to sort out the different frequency bands that we need to tackle for dynamic responses, but yeah, this is.
Okay, so but I have to wait until the next version of the documents to see your ideas.
Yeah.
Okay.
Vidman Tadrushas from Litgrid. Maybe I missed about timeline. When do you expect to finish
the task?
Yeah, to have final results.
The task will end in December this year. So the first version of the report was published a few months ago, and then there will be a revised version with the new materials that Pascal introduced at the end of this year. And then the InterOPERA project is running for 2 more years.
Yeah. Okay. And where we can find this publication?
On the InterOPERA website. InterOPERA website, yes.
interopera.eu.
Okay.
Tu peux reprendre.
Could you share this
Ouais, mais
presentation?
le chargeur ne marche pas, donc...
Non.
Enfin, je sais pas, c'est bizarre. Vas-y, rends-moi, mais...
I think so.
Take a question.
I think so. But I mean, it's been public. I don't see why we don't share the session.
Yeah,
for sure.
Sorry.
Yeah, for sure.
Yeah.
Would you send to registered participants or how?
I think we could.
Yeah.
If we have the list, yes.
So we have another.
Yeah, we can come back to this maybe afterwards. How we send it. Yeah.
We have a question from George Santos online. George, I don't know if you want to open your mic and ask your question yourself, but otherwise, yeah, that's the question for you. Okay, so the question from George was, what are the time parameters values for the expected from the DC party curves?
Yeah, that's an excellent question. So first of all, we wanted to make sure here that we have a consistent framework. The time specific time frames they need to be assessed. We would like to do this in the last stage, but for now we did not define this this clearly. Yeah, this is also for some values a bit critical, because they depend on solutions, and we need to assess what are reasonable values where all vendors can agree on. Also important to not only agree internally, so we need to agree on values that are convenient. But for instance, for the DCFRT specifically, we assessed, for instance, the undervoltage curves here. So as you can see, it's below 0, and this is reflecting on the voltage reversals of cable transients that we can have. We even assessed how different materials of cables influence this minimum values of the undervoltage values. and this is also already part of the first version of the deliverable, but we are still also working on it, and this is quite extensive studies that we did there, and will also be incorporated in the standalone tests of the converters regarding DC4 drive-throughs, and yeah, then also tests for the circuit breakers or the fault separation devices, because they should ensure to open for realistic DC4 transients, which is not only a step from nominal voltage to zero, but it should reflect on how these transients are effectively propagating in the DC system.
Follow-up questions to that, maybe. This DCFRT profile will be different for all the converters in the system, probably, because might be depending on the distance towards the next fault separating device, I would guess. And do you give recommendations in the document how to derive such all these values? Because I would be a system operator, and I want to use this, and obviously I want to make this project specific and provide the values with it, but I would say it's not a straightforward way to come up with these values. And do you provide recommendations for it?
Yeah. Actually, so first of all, it's a generic curve that is, for instance, applicable to each and every DC point of connection in the same way. So you would not.
Values are different.
Not necessarily. I mean, the voltage recovery time, for instance, it's a global parameter which is associated to the maximum allowed fault notification time of a circuit breaker in the given system. It's not associated to the closest circuit breaker, but to a global parameter. And then in this time range, you can have a huge variation of fault notification times, and the specification for the converter is only reduced to the recovery time, incorporating all possible fault notification times, for instance. Then when we go through it, we can also see this dynamic range. So this is then associated to the dynamic response of the converters during disturbances. We can also have you see here the static voltage range, so we can find some links and interdependencies which are unavoidable. So once we specify the dynamic voltage ranges, this directly provides us a guidance for this value, for instance. Same holds for the fault notification time. They directly give us a guidance on the recovery time when we have a clear idea in mind what is the security margin between the fault notification and the active DC voltage recovery. Yeah, system operator, I guess, would have some security margin as in AC, where circuit breaker does not open necessarily in 150 milliseconds, but still it has been chosen, and this is because you include maybe backup protection or any other unforeseen security margins. And, yeah.
There's a question online from Suresh Anturu, asking what are the synchronizing conditions to be able to connect two DC networks?
Synchronizing.
Yeah, that's the word you use.
Okay, but it's okay. Then it's a reference to the to this. No, before.
So now.
So the synchronization. Maybe the word is a bit misleading because it's not. I mean, it's not what synchronization is in AC, but the idea is that synchronization refers to a switching unit that will connect two live DC networks. So typically, if you have a point-to-point on one side, another point-to-point on one side, they are running, and you want to connect them during operation to form a HVDC grid, then what you expect is first to have a voltage level that is roughly the same on both sides before you connect, and you expect the switching unit to be able to endure the transient due to the small voltage mismatch that you will have anyway, and the small the current flowing in it. So yeah, synchronization refers to this ability to connect two live grids with two existing power flows. Basically, you can see that it's a gradation that aggregation means to connect two dead parts without voltage anywhere. Energization is having voltage on one side and not on the other side, and synchronization refers to having voltage on both sides. And this illustrates that the switching unit has a automation that is able to distinguish between those different kinds of situations only based on local information, because it can measure voltage on both sides and just choose or recognize in which situation it is. And if, for instance, you have a switching unit that is a very poor one without any ability to endure, for instance, peak current, only able to aggregate subsystems, then it may refuse commands to close if it actually requires energization or if it detects voltages, basically. So that's the whole spirit behind it. In the report, you will find more details about what's behind those different sequences.
No. Other questions? It's time, right?
Good for you. So thank you very much, Paul and Pascal. A very interesting presentation and discussion. For the people in the room who did not register via the QR code here, I recommend you do it if you want to get the presentation afterwards that we'll send directly to you guys. If there were any other questions, I mean, we would be happy to respond later on. I think most of you have the contact of Pascal and Paul, and if not, you will find it through the invitation that you received for connecting to the call. That's it for us today. Thank you very much again.
Thank you.